Video 3 for the nuclei and radioactive unit. So what are these rays really? So let's start with alpha. These are chunks of 2 protons and 2 neutrons. So we can think of it as the same as a helium nucleus. And they move at extremely high velocities. Beta rays. We can think of these as energetic electrons. No T in. No T in energetic. So they have about the same energy as a slow alpha ray. Gamma. These are packets of very energetic light. They're about 1,000,000 times as much energy as visible light. We'll spend a whole 2 units talking about light and invisible light. Neutrons, same mass as a proton. With no electrical charge. And these are not dangerous by themselves. However, they are needed to start nuclear reactions. So neutrons can do secondary. They can have secondary effects. X-rays. These are packets of light, like gamma. But they have about 10 to 100 times less energy. They pass through materials like carbon and water, but they are stopped by elements with a high atomic number, like calcium and lead. So this is why they're really good for taking pictures of inside your body, because our skin and tissues are usually made of carbon and water, but our bones are made of calcium. And then they throw a lead vest on your chest to prevent any of those from damaging any of your internal organs. Cosmic rays. This is any radiation from space. Usually, this comes into from protons, electrons, um, gamma rays, and something different called a muon. Fission fragments. This is the dangerous kind of radiation that's emitted when a nucleus undergoes fission. Now, fission really is just, when you take a nucleus of an atom, and break it apart, so it splits. So these are the broken fragments from the parent nucleus. They tend to have they tend to be radioactive themselves. So think of a nuclear bomb exploding. What happens is that the nucleus of each atom breaks apart. The fragments then are those pieces, and they can be very radioactive. We often call those particles fallout. Cathode rays. This was discovered emanating from hot metal. Had a high voltage applied. For a long time, we were really sure what cathode rays were. Turns out they were electrons. So that was kind of a surprise. Neutrinos. This is the most mysterious of all the rays. They are so strongly emitted by the sun that we have 10 to the 10 of these neutrinos passing through every cell every second. So that's something very, very, very important if you think about it. There are a lot of neutrinos passing through you right now. So really what we know is that they're not dangerous. They don't seem to interact with electric or nuclear forces. So it's not like they're busting apart your DNA or anything like fission fragments do. And then finally, this one's important, radiation from cell phones. These are actually microwaves. Cell phones use microwaves. And what's important to understand is that this is even lower energy than visible light. These microwaves do not break up DNA. They pose no risk whatsoever. So use your cell phones in confidence. They are not harming you. Same way goes with the microwave oven in your home. It is invisible light, So it's very similar to visible light, but it has even less energy than visible light. All right, you, yes, you are radioactive. So a typical human body contains about 40 grams of potassium. Most of this obviously is stable, non-radioactive isotope potassium-39. So most of the 40 grams in your body is potassium-39. But about 0.01% of all of that 40 grams of potassium has an extra neutron. So it's potassium-40. Potassium-40 is radioactive. So if we think about it, it's 0.01%. So that's 40 divided by 10,000. Potassium-40. This potassium-40 is radioactive. It is a cancer-producing isotope. At 0.004 grams, so you have roughly 6 times 10 to the 19 atoms that are cancer-causing radioactive atoms. So that's quite a lot of atoms. Approximately 1,000 atoms of potassium-40 explode in your body every second. About 90% of these explosions produce an energetic electron, a beta ray. Most of the rest produce an energetic gamma ray. So this radioactivity within your body produces a dose of right around 0.016 rem over a 50-year period. That's not a lot. So take 0.016 and divide that by 50 to get how much REMs you're exposed to per year from your very own potassium-40. So how does this affect your chances of getting cancer for yourself? Well, what we do using the linear hypothesis, we take our 0.016 rem, we divide that by the cancer dose, 2,500 rem. So that gives us 6.4 times 10 to the negative 6th. So because of your potassium, you get another 6 chances in a million to get cancer. You have the better luck of winning the lottery. So even though you are radioactive, the radioactivity it does not influence how much your chances of getting cancer. So how about the U.S. population as a whole? There are 300 million people in the U.S. So if I take those chances, the 6 point, or might as well round it to 6 times 10 to negative 6, that equals 1,800 people. So we expect 1,800 people to die within the next 50 years from self-induced cancer. So basically another 36 per year. However, remember that we expect 20% of the population to die from cancer anyways. So, when we run those numbers, that's like 60 million. So um, comparing 1,800 versus 60, um, it doesn't really make sense that the potassium in your body would be causing any kind of extra, cancer deaths to begin with. All right, kind of a morbid topic, so we will finish up there, and in our next video we will start talking about radiocarbon dating.